Okay, this is midterm review part 3, number 9. Two fair dice are tossed, one is red, one is green. Calculate the probability the sum of the numbers is odd given that the red die value is larger than the green. So that we have the probability the sum is odd given that we know the red die's value is bigger than the green. So conditional probability, it's the probability of the intersection divided by the probability of the given. So it's the probability the sum is odd and red is greater than green divided by the probability the red die is bigger than the green. There's 36 total outcomes when you roll a pair of dice. There are 6 times where the values are the same, and the remaining 30 they're different, split equally. So half the time the red is higher, half the time green is higher. So the probability that red is bigger than green is going to be 15 out of 36. So we're basically counting of those 15 where the red is bigger than the green, how many of those have an odd sum? So basically, in order to get an odd sum, you need to have one odd number and one even number. So I just ran through the cases here. So red first and then green. So we need the first number to be higher than the second. So 2 plus 1 makes an odd 3. Now, if you start with a 3, 3 and 1 would be an even. So we skip that. It's got to be an even number. 3 plus 2 is 5. Again, 4, we have to pair it with an odd. 4 and 1 and 4 and 3, those add up to odd numbers. 5 2, 5 4, 6 1, 6 3, 6 5, for a total of 9 ways. So there are 9 ways here to get an odd sum where the red is bigger than the green. So the probability is gonna be 9 out of 15. So the probability that red is bigger than green is 15 out of 36. The probability that we have an odd sum and red bigger than green is 9 over 36. The 36's cancel out. It's 9 over 15, which is 3/5. In many cases in these problems, we can ignore the grand total number. As long as we're careful that we're setting it up out of that common denominator total. There are 15 ways for red to be bigger than green. That's your denominator. Of those 15, within that set of 15, how many satisfy the second condition, some being odd? That was 9. 9 out of 15 reduces to 3/5. All right, number 10, the profit for a new product is given by z is equal to 3x minus y minus 5. X and y are independent random variables. Variance of x is 1, variance of y is 2. Find the variance of z. So because they're independent, we can add the variances. So the variance of t plus s is variance t plus variance s. And then we have another property here that the variance of ax plus b is a squared times the variance of x. Adding a constant does not affect the spread, so that does not have any impact on the variance. Multiplying by a, remember the variance of the squared errors there, so it becomes a squared times the variance of x. So what's the variance of this new variable z, 3x minus y minus 5? Well, we can do them individually. So it's variance of 3x plus the variance of negative y minus 5 because we were told they're independent. Variance of 3x, the 3 comes out as 3 squared times variance of x. The variance of negative y minus 5, the minus 5 has no impact. We have to take that minus 1 and square it, which comes out to a positive 1. So we're left with 9 times the variance of x plus the variance of y. Variance of x was given as 1. Variance of y was 2. So 9 plus 2 is 11. The variance of this new expression, z, is 11. So we're using the properties of variance here to simplify this. All right, 11 is Bayes' theorem. So a person is known to speak the truth 3/4 of the time. The person draws a card and reports it's a king. Find the probability is actually a king. So what are the two cases here? A king was drawn and the person told the truth, or the king was not drawn, which indicates a lie. Let D represent that the king was drawn. Let R represent that the king was reported. So two different things here, what the card actually was and what the person says it is. So D is the king being drawn, and R is the king being reported. So we want to know the probability that the king was drawn given it was reported. A card was drawn. We don't know what it was. It was reported a king. What's the probability it was actually a king? So we want the probability king was drawn given that it was reported. So we do the reversal and Bayes theorem here. It's the probability of R given D times probability of D divided by that same expression plus the other case here. It's only two cases. It's either a king or not. Probability reported given not drawn times the probability of not drawn. Now, what's the probability of drawing a king? The probability of D drawing a king, that's 4 out of 52. What's the probability of not drawing a king? That's 48 out of 52. Now, the other parts here are basically whether or not it's a lie or the truth. So, the probability of R given D of reporting a king given that was a king, given a king was drawn, that would be that would be speaking the truth. So that's 3/4. A king was not drawn, and then if a king was not drawn, it means the person lied. So that's this expression down here. The probability of reporting a king given that it was not drawn, it was not a king, that would be a lie, and the probability of that is the opposite, is 1/4. So just to recap, the probability of drawing the king is 4 out of 52. Probability of the negation, not getting a king, 48 over 52. The probability of R given D, reporting a king given it was a king, that is telling the truth. That's 3/4. Reporting a king when it was not drawn is a lie. That's 1/4. We have a common denominator here of 4 times 52 that we can essentially multiply through and cancel out. That leaves us with 12 over 12 plus 48, 12 over 60, which is 1/5. So there's a 1/5 chance that it was actually a king, given that the person reports it's a king. All right, number 12. Back from one of the early lessons here, permutation with duplicates. Find the number of different words formed using the letters 13. So we have a total of 8 letters here. So that's 8 factorial divided by the duplications. There are 2 copies of E and 2 copies of T. So it's 8 factorial over 2 factorial, 2 factorial, which is 10,080. 13. This one's a little trickier. How many odd 4-digit numbers have all different digits? So a couple of things here. When we say a 4-digit number, we don't want to allow starting with a leading 0. That's the first thing. So we're not going to allow a leading 0. And in order for a number to be odd, its last digit has to be odd. So starting there are 5 odd numbers. So there's 5 choices for the last digit. The first digit cannot be 0 and cannot be the same as the last digit because they have to all be different. So that leaves 8 possibilities there. Then the second digit has to be different from the first and last. It's allowed to be 0, so that's in play. So that also has 8 choices because it could be the 0. And then the third digit has to be different from all the other ones, and so there's 7 choices left there. So the total number of ways to achieve this here, total number of possibilities, is 8 times 8 times 7 times 5, which is 2,240. So again, to recap, we have 5 slots for the last digit. It must be odd. Now, the first digit, we have to avoid whatever the last digit was, plus we can't have a leading 0. So that's 8 possibilities there. The second digit, we just have to avoid whatever we put down in the last and first spot. So that's 8. And then the third digit, we have to avoid the other 3. That's 7. We multiply it all out, 2,240. All right, this is going to be one extra question for the graduate students. Will involve some type of proof of expected value or variance. In this case here, we're asked to prove the expected value of a binomial random variable with n trials, and probability of success p is n times p. The expected value of a Bernoulli random variable is p. And then we're going to view a binomial as a sum of Bernoullis, and then we just add that up. So remember to recall a Bernoulli, it's just basically a single trial, either a 1 or a 0. Probability of a 1 is p. Probability of a 0, this should be 1 minus p. Let me just cross that out there. It doesn't affect anything because it is multiplied by 0, but that's incorrect there. Unfortunately, I can't edit that. It's supposed to be 0 times 1 minus p. Sorry about that. So the probability of getting a 1 is p and getting a 0 is 1 minus p. Adding that up, it's just the expected value is just p. So now we can view the binomial as a sum of Bernoullis, and then the expected value of a sum is the sum of the expected value. So you just add up that same value p, you just add that up n times. You add that up n times, and you get that the mean of the binomial, expected value of the binomial, is np. So you don't have to do the longer method of doing it directly here. You can use the fact that it's a sum of Bernoulli. Each one has expected value p. There's n of them. Summing that up, it's n times p. All right, this concludes the review sheet here. Please, if you have any questions, don't hesitate to send out an email or post in the discussion board. Thank you.